Hello everyone, my name is Ian and the topic of the day is Thermodynamic Evaluation and Sustainability Analysis of Entrainer in Extractive Distillation. So to start off, what is extractive distillation? It's a specialized distillation technique used to separate azeotropic liquid mixtures that cannot be separated using conventional distillation because of their vapor and liquid composition become identical at a certain point. How does it work? We introduce a third component called an entrainer or a solvent, and this entrainer selectively interacts with one of the components in the mixture, altering the liquid phase activity coefficient and increasing their relative volatility without forming a new azeotrope. What's the difference between extraction and extractive distillation? So one of the differences are liquid extraction relies on chemical solubility differences and phase separation, whereas extractive distillation relies on modifying vapor-liquid equilibrium, which is VLE, through solvent addition. So why do we need an entrainer for ethanol and water specifically? At atmospheric pressure, the ethanol water system forms a minimum boiling azeotrope at 95.6 weight percentage ethanol. At this exact composition, known as the azeotropic pinch point, the relative volatility drops to 1.0, which means that the vapor composition equals to the liquid composition, making it further separation by standard distillation physically impossible. Looking at this data generated from Aspen Plus, you can clearly see that when the ethanol mole fraction approaches 90 mole%, the boiling temperature flattens out around 351.3 Kelvin and the K value approaches around 1. So this confirms the pinch point where separation stops. So this is the same thing as you can see based on the graph around 0.9. The two lines are merged into one, which means azeotrope has been formed. So the main purpose of this study is to evaluate the solvent to feed ratio impact on relative volatility of ethanol water using glycerol and ethylene glycol, and to analyze the solvent to feed ratio impact on solvent selectivity, and then compare the thermodynamic data performance to determine the superior entrainer. So the reason why I am doing this is to identify which one is more efficient and sustainable entrainers for an industry in bioethanol production. So to analyze this system, we set up a thermodynamic framework under some assumptions, which are the atmospheric pressure at 660 mmHg and ideal vapor phase and non-ideal liquid phase, and a single stage equilibrium threshold. So here are the list of formula used, which are modified Rhodes law, extended Antoine equation, NRTL activity model, and the two main indicators, which are relative volatility, which measures how easily ethanol separates from water, and solvent selectivity, measuring the ratio of ethanol to water in vapor. These are the software tools that I use in calculation and validations. The first is Microsoft Excel to perform a lot of iteration, and Aspen Plus in order to validate my results and calculation. This is the step-by-step calculations and also the parameters needed to perform the Yaws Antoine equation, and also the NRTL parameters that are sourced from Aspen Plus to calculate activity coefficient. So the first thing to do is to specify the feed composition and also the solvent to feed ratio, and then guess and iterate the bubble point temperature and solve the Antoine equation based on the Yaws handbook. After that, using the NRTL model to calculate the activity coefficient for each component. You can see here, I use the new saturation pressure and reiterate to find the total pressure as 760 mmHg, which is 366 Kelvin, and this will be applied to all the solvent to feed ratio. After doing iteration, the table is being made to see the result based on graph. This is the part where we do parametric sensitivity evaluation. As you can see, at solvent to feed ratio 2.0, glycerol reaches around 7.58 and ethylene glycol reaches around 5.48. And in terms of solvent selectivity, at solvent to feed ratio 2.0, glycerol reaches around 3.39 and ethylene glycol reaches around 2.43. So what we can get from this graph is that glycerol outperforms ethylene glycol across all tested points. To ensure our Excel model was accurate, we validate our findings against Aspen Plus simulation. As you can see, there are differences in terms of the value. However, that is due to Aspen's advanced equation solvers, and the percentage relative error is quite low, and also the thermodynamic conclusions and relative rankings remain consistent. As you can see, the graph generated by Aspen Plus proves that both entrainers successfully break the azeotrope. So which entrainer is better? From a purely thermodynamic and environmental standpoint, glycerol is the winner. Based on the molecular structure, glycerol has 3 hydroxyl groups compared to ethylene glycol, and this allows glycerol to form a stronger selective hydrogen bond with water, which pulls the water into the bottom product and boosting the ethanol vapor purity. In terms of sustainability, glycerol is a renewable non-toxic byproduct of biodiesel, which has a negligible vapor pressure of 0.304 mmHg, meaning there is no solvent is lost in the distillate vapor. However, engineering is always about balancing ideal thermodynamics with real-world physics. So pure glycerol has a higher dynamic viscosity, In a full-scale industrial column, this high viscosity increases fluid pumping resistance, lowering mass transfer rate, and increases the reboiler heat duty. Therefore, industrial best practice often favors a compromise using a 60% ethylene glycol and 40% glycerol blend. This hybrid approach captures the high thermodynamic efficiency of glycerol while maintaining a manageable fluid hydraulics and lower operational energy costs, which is proven by Navarrete, Contreras, and Cowell. So, what we have learned today is extractive distillation effectively breaks ethanol water azeotropic pinch point, and glycerol is thermodynamically superior to ethylene glycol. And the real-world application requires balancing thermodynamic efficiency against fluid, hydraulics, and reboiler duties. Thank you very much for your time, and the bottom right is the references to this study.